Math 13 students, hello. We have a video here on some linear regression detail. We're going to take a look at finding the linear regression equation, and then we're going to take a look at how we use it. The very nice thing here is I really don't need to show you any new keystrokes. The linear regression equation is found every time we do a test for linear correlation. So the keystrokes that we'll use in 10.1 are the same keystrokes we use in 10.2. In fact, the keystrokes in 10.1 also answer the 10.2 questions. So follow me over to my other screen and we'll go through the detail. All right, chapter 10. Let's see, what do we have here? 10.2, finding and using the regression equation. So, a little bit of an outline. In this presentation, we're going to review the notation for a regression equation, remind ourselves what we're looking at. We'll take a look at the tools that we'll need to find that regression equation, and then we're going to use that regression equation to make one or two predictions. And those are going to be the appropriate examples that we explore. So let's review the regression equation. So a regression equation basically defines some sort of association, not necessarily causative, between two variables, or even more, x and y in our case. There are many different kinds of regression equations. Linear, quadratic, and exponential are perhaps the three most basic and common. Here we just look at the linear model. And this really riffs right off your y equals mx plus b detail that you encountered in your algebra courses. The notation, though, is a bit different. When we take a sample x and y data set, and we do the regression equation, we'll use y hat equals b naught plus b1x. Things have been changed around and renamed, but at the end of the day, the y-intercept is b naught and the slope is b1. Now, it's important to remember that your sample is really just an approximation of a population parameter. In this particular case, we have a population regression equation that we're trying to essentially estimate with the y hat equals b naught plus b1x. And very much like other instances when we talk about population parameters, we like the Greek letters. So the population regression equation for the xy population would be y, no more hat here, equals beta naught plus beta 1x. That thing that looks like a funky B is the Greek letter beta. The y-intercept is beta naught, and the slope is beta 1. And again, we have this y equal mx plus b renamed and rearranged. Now, let's talk a little bit about the process. Your calculator does a wonderful job in finding this regression equation. It will do this every single time you test for correlation. However, there are differences in notation that need to be addressed. Your calculator likes y equals a plus bx. We'd have a y-intercept of a and a slope of b. Your text likes y hat equals b naught plus b1x. And you'll remember from your algebra sequence of courses, y equals mx plus b. So you can see that the coefficient for the x is the slope, regardless of what we call it, b, b1, or m. The constant value, b, b naught, or a, is always the y-intercept there. So at the end of the day, we like to input the data and draw the scatter plot. I always like to take a visual look at the data before I run down any linear regression blind alleys. Once I get that plot drawn and I notice a reasonable linear relationship, I'll test for correlation. And the reason I'll do that here is so I can pull out the regression equation. I'm going to write that down, and then I'm going to go ahead and use that regression equation. All right, so here's our example. Age and income are closely related. The older you are, usually a little bit more you make. So we're going to have some data on age and income, and we're going to do a couple of things. We're going to find the regression equation, and then we're going to use that regression equation to predict the income for someone 55 years old. So we have some age and we have some income. $28? No, $28,000. So realize your age is in years and your income is in thousands of dollars. Here's our data. So the first thing we'll do is input the data. Then we'll draw the scatter plot, we'll test for correlation, and then we'll note the regression equation. So let me go ahead and run the video and take a close look at the keystrokes. So I put my data in my calculator, list 1 and list 2. You've seen me do that many times before. I don't think you want to see me do that again. I'll go to stat plot and I'll select plot 1. I need to make sure it's turned on. If off is selected, I'll need to go down and make sure I hit enter to select on. Now you'll notice the on is flashing. Then I'll use my arrow keys to select my appropriate list. They're already there. And then I suppose the color, if I want to change that, I can do that. The most important key is zoom 9. This gives you the appropriate window for your stat plot. So now you've got that linear graph there. You can now go ahead and run the test. You'll use linear regression t-test or linreg t-test. It's way down near the bottom. The semester is almost over. It's like, in fact, it's past all of the numbers and it's into the letters. D or something? No. E? No. F? Yes, F. So linear regression t-test, it asks you for a list. You'll leave the frequency at 1. You got to give it 2, 1 for the X and 1 for the Y. Remember, this should be set at not equal to 0. All these tests are two-tailed tests. Now, I notice at the top of the presentation, I see Y equals A plus BX. And a little bit further down, I see A equals a negative 4 and change, B equals 1 and change. So I have my y-intercept and I have my slope. And I'm going to use the appropriate notation. So y hat equals a negative 4.9 plus 1.2x. I'll take 2 decimal places here. There's no hard and fast rounding rule when it comes to linear regression equations. So there's our equation. Came right out of the linear regression t-test tool. Now, we're going to go ahead and run through using that regression equation. We're going to use that regression equation to predict the income of someone who is 55 years old. It's pretty simple. All we need to do is to let x equal 55. When I plug that into the regression equation, oh, I got a typo in there. It should be a negative 4.9 plus 1.2 times 55 equals 61.1 or $61,000. So do note that should be a negative there. We got a typo. I'm going to let it fly for now. There are issues, though, with the regression equation. Predictions should be made only for x values that really fall in the range of your sample data. I think the youngest person in that table was 23 years old. We run into issue when we move far outside that range of age. For example, if I want to predict the earnings of a 7-year-old, there's the negative. So young for work. But when I run through that set of calculations, it turns out that my 7-year-old could earn $3,500 a year. This is extremely, extremely unlikely. You really can't rely on that particular sort of prediction because the x value is so far outside the range of all the other x values. So that puts a bit of a limitation on where you can really count on the validity of your estimate or your prediction for the y value. You want to keep the x close to the other x's. So we have reviewed the notation for the regression equation. We took a look at the tool that we'll need here. We used the regression equation to make some predictions after we found that regression equation using the linear regression t-test tool. And we took a look at a couple of examples and we saw some real limitations to our regression equation and where we are supposed to use it. So I will say goodbye for now. I will thank you. That is the end of this presentation. I'll stop the sharing. I'll ask that you show up at the office hours, come to me with keystrokes. 10.1 and 10.2 really, really, really go together. So you almost want to do them back to back. So goodbye for now, and we'll see you later.